Good evening, Chem Kids. This is a video on Chapter 13, Gas Laws. I thought we'd go over the review. Let's look at some of these questions. Charles' law deals with volume and pressure. Well, you know that Charles' likes to watch TV. So Charles is dealing with volume and temperature, not volume and pressure. So that would be false. And gases are the most compressible states of matter. You need to know that that is absolutely true. Atmospheric pressure at sea level is 1 atm. That is true. Standard pressure is not 1 torr, it's 1 atm, so that is false. Gas laws can be calculated in Celsius. They can never be calculated in Celsius, only in Kelvin, so that is false. The constant 0.0821 appears in Boyle's law. No, it appears in the ideal gas law, so that is false. Atmospheric pressure varies with altitude. That is absolutely true, and you need to know that. In Boyle's law, the volume and the pressure are not directly related. They are inversely related. That is false. Gay-Lussac's law states that the pressure of a gas is directly related to the temperature in Kelvin. That is true. Remember, Gay-Lussac likes to drive a PT Cruiser, pressure and temperature. 1 gram of any gas at STP takes up a volume of 22.4 liters. Looks tempting, but it isn't 1 gram, it's 1 mole. So that makes it false. Okay, let's look at this next problem. This next problem has to do with moles. And they give you a pressure and a temperature. So that's going to be the ideal gas law. That's PV equals nRT. You're going to be solving for volume. So volume is equal to nRT over P. And you're going to put everything in there. Don't forget to change the 90 degrees Celsius into Kelvin. And that problem is worked out in the answer key that I posted. But that's how you decide what law it is. This next law involves volume, pressure, temperature, which you're going to turn into Kelvin. That's 293 Kelvin. And they want to know what happens to the pressure when the temperature decreases. This 4 liters is very interesting here because if you notice, they didn't mention the 4 liters again. That means that the volume in this problem didn't change. So the volume started off at 4 liters and ended up at 4 liters. So therefore, the 4 liters is a constant, and this problem is just about pressure and temperature. So this is Gay-Lussac's law because it's just about pressure and temperature. Okay, looking at number 13. Number 13 is all about moles, volume, temperature, and pressure. And therefore, this is the ideal gas law, where we're solving for moles. So N equals PV over RT. The solution again is in the answer packet. In Boyle's law, number 14, what variable is constant? Well, Boyle is about P and V. And so what has to remain constant is temperature. Another choice that would have been okay here would be moles. The moles and the temperature are constant, but they didn't mention the moles. So temperature is the best answer there. Okay, 15, I'm going to switch colored pens, is about volume, temperature, and that is Charles. And again, the full solution to that is in the answer packet. Number 16 is about volume and pressure. That's going to be Boyle's law, and that's how you tell. Number 17 is very important. What does the ideal gas law allow a scientist to calculate that the other gas laws do not? That would be the moles. That's what makes the ideal gas really different. The ideal gas law, even though all of these are correct, the ideal gas law is usually written as PV equals nRT this way. And number 19, don't forget to change the Celsius to Kelvin. It's negative 78. So we're going to subtract 78 from 273. They want the volume. So this is about volume and temperature. So this is Charles's law. And again, the solution is in the answer packet. Number 20, at constant pressure and number of moles, the volume and temperature of a gas is directly related. So they're really asking you to leave out the pressure and moles because they're telling you that they're constant. So really they're asking whose law talks about the relationship between volume and temperature, and that would be Charles. Okay, you need to know that a direct relationship is always a straight line, so that would be A. Which of the following is the correct arrangement of the combined gas law when you solve for T2? Here's the combined gas law. V1 P1 over T1 equals V2 P2 over T2. The best thing to do here is to cross multiply, and we get V1 P1 T2 equals V2 P2 T1. And again, the problem wants you to solve for T2. So isolating T2, we divide out by V1 P1, both sides, and you get T2 equals V2 P2 T1 over V1 P1. And that corresponds to choice number D. Okay, the next problem, number 23. Number 23 gives you a volume, the milliliters, and it gives you a temperature, and it gives you a pressure. And so it has all of them, so this is going to be the combined gas law. And again, the solution is worked out in the answer key that I published. Number 24, remember that I'm going to give you all the relationships, and anytime they mention a mixture, that's going to be a key that you need Dalton's law, because it's a mixture of gases, and it's all the numbers in the problem are pressures. There's no volumes, there's no temperatures, just a lot of pressures. Again, the solution is in the answer key. All right, number 25, the conditions under which gases behave most like ideal gases. Remember, we were talking about when is a gas most like a gas. And a gas is most like a gas at very, very high temperatures and low pressures, because the particles can be very far apart. So that is the most. And if I asked you when is a gas least like a gas would be the opposite, would be at low temperatures and high pressures. All right, number 26 is PV equals nRT, where you're solving for moles, but the twist is STP. If you can't find a temperature and a pressure, that's because it's hidden in the words STP. Remember, STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atm. All right, on 27, they want the answer in grams. So you have to solve for moles, PV equals nRT. You have to first solve for moles, N equals PV over RT. And then once you get the moles, you have to turn the moles into grams by multiplying times the molar mass over 1 mole. And again, the key has the solution worked out. In 28, it's the reverse. They give you the data in grams, so you're going to change 15.8 grams of ammonia, and you're going to change that to moles by multiplying by 1 mole of ammonia is equal to 17 grams, and then that is going to be your answer in moles, which is N, and that's what you're going to use in the formula PV equals nRT. You're solving for V this time, so V equals nRT over P, and the solution is in the key. Now, this is just to remind you that you need to do a manometer problem on the test. There's only going to be one, and remember that the side that's lowest has the greatest pressure. That's what you need to remember. Okay, let's go over the characteristics of an ideal gas. An ideal gas does not really exist. All the gases in our life are real gases. But an ideal gas is, you have to assume that the particles are very small, that they're point particles. They're very tiny, they're very far apart. And when ideal gas particles collide, they don't lose any energy. Those kinds of collisions are called elastic collisions, and no kinetic energy is lost in elastic collisions. Gas laws are always moving. They're always moving in constant, rapid, random motion. Gas law particles that are ideal do not attract each other in any way. Once they start to attract each other, they start to become a liquid and clump up. This is very important. The average kinetic energy of a gas particle depends on temperature, not on the kind of gas that it is, not on the identity, but on the temperature. These graphs you need to recognize. This is Boyle's law. This graph is an inverse relationship because, as you can see, as the volume is increasing, the pressure is decreasing, and that relationship we say is inverse. So pressure and volume are related inversely. Almost all the other relationships in gas laws are direct. Speaking of direct, we have a graph here. This is the graph. Right now, it's the graph for Charles because it's volume and temperature. But if volume were replaced by pressure, then this would be Gay-Lussac's graph. And this is a straight line. As the temperature increases, so does the volume. And that kind of relationship is direct. So volume and temperature and pressure and temperature are direct. The way you can think of that is anything associated with temperature is going to be a relationship that is direct because temperature is such a strong driving force in chemistry that it drives almost everything in its direction. This is the ideal gas law, and we already know that the relationship between P and V is inverse. We already know that the relationship between V and T is direct. We know that the relationship between P and T is also direct. But how about V and N? How about V and moles? Well, Avogadro's law tells us that that relationship is also direct. Right here, the volume of a gas is directly related to the number of moles. Avogadro also said that if you have 3 different gases, or 4 or 5, but you keep the pressure and the temperature the same, even though they have a different mass, they're all going to have the same number of particles. That is also part of Avogadro's law. Dalton's law. Dalton's law says that the total pressure in a system is given by the sum of all the different gases that are in there. So if you look at this canister, the entire pressure in the canister is given by this one gas because there's only one gas in there. But here there's 4 gases. And so the total pressure is the sum of pressure A plus pressure B plus pressure C plus pressure D. All of them. All of them go to make the total pressure. This is the problem that we worked on in class. You can take a look at that. This is what we were talking about a few seconds ago, and that is the deviations. When is a gas most like a gas? We said that a gas is most like a gas, so most ideal. A gas is most ideal at high temperatures and low pressures. And the way to remember that is anything that keeps the particles far apart and moving fast is going to go towards making the gas more ideal. And less ideal, okay, least ideal, again, is the reverse, which is low temperatures and high pressures. And that's going to bring the molecules together. And once they come together, what takes over are these attractions. It's the attractions that make the particles clump up and act like the next state down from a gas, which is a liquid. All right, this is a great graph because this is the same gas at different temperatures. The purple is at a lower temperature, the green is at a higher temperature, and the red is at a highest temperature. If this dotted line is ideal gas, then you notice that at the highest temperature, the gas behaves the most ideally. This is Graham's law. This is Graham's law of diffusion and effusion. The difference between diffusion and effusion is diffusion is the gradual mixing of molecules from one side, from a site of greater concentration to a side of lesser concentration. But effusion is the movement of molecules from one area to another by passing through a small pinhole. And one of those areas is under pressure, kind of like an aerosol can. Graham's law says that it's comparing the rates of gases, and Graham's basic idea is that lighter molecules travel faster. So that if you're comparing the rates of the one gas to a second gas, it's inversely proportional to the square root of the masses, meaning that if V1 is on top, then M1 is going to be on the bottom here. And if V2 is on the bottom, that means the mass of M2 is going to be on top. Again, here are a couple of problems that we worked on in class that show very good examples of those. These are all the laws. So I'm going to give you the laws, but I'm not going to tell you the names. So we can see that this one, PV, Boyle is the vice president, so this is Boyle's law. This is the ideal gas law because it has moles. This one is Gay-Lussac because it has P and T. So remember, Gay-Lussac likes to drive a PT Cruiser. This is Graham's law because it has the square root of the masses. This has P, V, and T. So this is called the combined gas law. P tote is Dalton. V and T, remember Charles likes to watch TV. And you have to know what STP is. Remember, STP standard temperature is 0 degrees Celsius or 273 Kelvin. And standard pressure is 1 atm with that entire string of things that 1 atm was equal to. It was equal to 101.3 kPa, 760 mmHg, 760 torricellis, 14.7 psis, and all of that I'm going to give you. Okay, remember to turn grams to moles, you have to divide by the molar mass. Also, you have to know the difference between a barometer and a manometer. And a barometer measures, the difference is what they measure. This measures the atmospheric pressure. And the manometer measures the pressure of a gas in a canister of gases other than the atmosphere in some kind of pressurized tank. Okay, so some other gas, not the atmosphere. Like a tank of carbon dioxide or oxygen. All right, remember that pressure is something that varies with altitude. The higher up you go off the earth, the less the pressure you have. And that's about it, everybody. I'm available through email. I will see you tomorrow.